first part of our electricity portion is this one, electricity and magnetism. So simple magnetism and magnetic fields, right? I'm just reviewing this for you. Okay. So what's happening is basically that we know that if we talk about a magnet, it is going to have two poles. I'm going to go really fast here. Okay. So firstly, if you talk about a magnet having two poles, it has a north magnet and a south magnet. And if you're going to support it such that it swings, okay, it's going to rest with its north pole directing towards its north pole, okay, and south pole definitely directing towards the south pole, okay. So this is how you can identify the north pole of Earth, okay. The north pole of your magnet is going to align with the north of Earth, okay. Actually, now if we talk about laws of magnetic poles, we have really easy laws, okay. We know that like poles are going to repel and then like poles are going to attract, and you need to know the magnetic fields that they seem something like this. If you have like charges, their magnetic field lines are not going to meet at any point, okay. But if you have unlike charges, they're going to attract, and always your field lines move from north to south, okay. And if we talk about just the north, then outside from north and inwards for south, okay. So these are the magnetic field lines, and you need to remember them, okay. Then moving on, we have two kinds of materials, okay. So first of all, we have magnetized materials, and then we have unmagnetized materials, okay. If you talk about magnetized materials, of course, if I'm talking about a material, okay, I'm not sharing screen, wait. Okay, so if I'm talking about a material that is magnetized, so it has a quality to both repel and attract, okay, because it is magnetized, right? So magnetic materials will always be attracted to the magnet regardless of which pole is held close to it, okay. This is how you can identify magnetic materials, okay. But if you talk about unmagnetized materials, okay, so they can be attracted to a magnet, but they will never experience repulsion, okay. So this is how you can identify magnetic materials and unmagnetized materials, that if you're talking about magnetic materials, they will always be attracted, and if you're talking about unmagnetized materials, so they can be attracted, but they will never experience repulsion, okay. Now a magnet can only repel another magnet, okay. So this is a very important point. The only sure test of a magnet is repulsion, okay. So magnetic materials are going to do what? They would always be attracted to a magnet. Unmagnetized materials can be attracted, but they will never experience repulsion, ठीक है. इसके अलावा for magnet, always repulsion for another magnet, ठीक है. So magnetized versus magnetized materials can both repel and attract. This is because they themselves are a magnet and so have poles, right? So this is why they can both repel and attract. If you talk about a magnet, it can only repel another magnet. If you talk about unmagnetized materials, they can be attracted, but they will never experience repulsion. If you talk about non-magnetic materials, they're not attracted or repelled, as they're not going to interact with the magnetic field, okay. Now moving on, we have induced magnetism. So induced magnetism is simply the idea that if you have a magnetic material, you can convert that to what? You can make an induced magnet, okay, by bringing it under the influence of a permanent magnet. So this is what we're doing right here, okay. We have a magnetic material, and when we're going to bring that near a permanent magnet, that is going to induce this pole on the opposite end, okay. So for example, in this case, we have north pole, so it's going to induce this north pole on the opposite end, okay. So this is what's going to happen. So if we look here, we also have a diagram, okay. What we can see is that, see, if we have two iron nails, okay, iron is what? Iron is a magnetic material, okay. So what's going to happen is that, again, it's going to induce make it an induced magnet, iron, okay. And so north pole, if it's north pole here, then it's going to be north pole on the opposite end, right? So if this is north pole, then we have north pole here, right? So what's going to happen is north pole here, north pole here, so repulsion between them, so that is why they are, this is the case here, okay. And now if you're going to increase the strength of the bar magnet, of the permanent magnet that you're using to induce this magnetism in the magnetic material, you can see that there is greater repulsion, okay. So this is the idea of induced magnetism. Then we have two types of magnets. We have temporary magnets and we have permanent magnets, okay. So basically we know that iron is going to be a magnetic material that will lose its magnetism easily. So it's basically temporary magnets are made up of soft iron, okay. So they lose their magnetism easily. Then we have permanent magnets, which is basically steel, and these materials are going to retain their magnetism. Basically, we learned about iron and steel, that if you talk about iron can be magnetized easily, and it will also lose its magnetism easily, okay. And if you talk about permanent magnets, it can be it will be difficult to magnetize it, and it will be difficult to demagnetize it. Okay, so this is the case for permanent magnets and temporary magnets. As you can see, what's going to happen. Okay, so if you have north pole here, it's going to induce north pole on the opposite end. Okay, again north pole on the opposite end, north pole on the opposite end, north pole on the opposite end. Okay, the same for these paper clips as well. Okay, because they both are magnetic materials. But because iron is a soft magnetic material, what is going to happen that when you're going to remove both of these chains, steel is going to retain its magnetism, so the iron clips will remain attached. Okay, but if you talk, because steel is a hard magnetic material, but if you talk about iron nails, then when you're going to remove it from the influence of this permanent magnet, it's going to lose its magnetism and the iron nails are going to fall. Okay, so this is the idea. Now whenever you talk about a field is always going to be a region where a force is experienced by a particle. Okay, so if I'm talking about magnetic field, I'm talking about a region of space in which magnetic force acts. Okay, so okay, and we also be discussing the direction of magnetic field. If we talk about direction of magnetic field at a point, then that will be direction of the force on the north pole of a magnet, right? So whatever is the force on the north pole is the direction of magnetic field in that particular, at that particular point. Okay, and you need to know this experiment too. Now the space surrounding a magnet where it produces a magnetic force is called a magnetic field that I just talked about. The force around a bar magnet can be detected and shown to vary in direction using the apparatus. If the floating magnet is released at the north pole of the magnet, okay, so this is the floating magnet, so what is going to happen? Okay, it's going to be repelled, right? So it's going to be repelled towards the south pole, right? So it is repelled to the south pole and moves along a curved path. Okay, so why is it moving around a curved path? Because of the idea that this is basically north pole, so there is going to be repulsion, and because field lines are always from north to south, right? So it's going to move towards the south pole. Okay, then what's happening? It is useful to consider that a magnetic field has a direction, and to represent the field is always going to be a vector field. Okay, and to represent the field by lines of force, it has been decided that the direction of a field at a point should be the direction of the force on a north pole. So basically, the direction of force on the north pole is a curved path here. So that is going to be my field line. Okay, to show the direction, arrows are put on the lines of force and point away from a north pole towards the south pole, right? So your apparatus for detecting magnetic force included a bar magnet, a cork. Basically you have made this magnet a floating magnet here. Okay, and for that you have a bowl of water, and you have cork, and you have attached magnetized steel needle or rod to make it a floating magnet. Okay, now what's that? Strength of magnetic fields. So if you talk about magnetic field lines, they're going to be stronger in regions where the field lines are closer together. Definitely field lines are going to be closer together, they are the bar magnet. Okay, so this we had already discussed it. How are we going to make field lines? If we put a plotting compass near the north pole of the bar magnet, what's going to happen? It's going to eventually make a curved path. Okay, so what we're going to do is that basically we're going to take a magnet, put it near the north pole, we're going to see where it's pointing, we're going to put a point there. Then at the point we're going to put our plotting compass again, we're going to see where its needle is pointing, then we're going to put a point there again. Okay, so when we're going to keep doing that, we'll see that will form a curved line. Okay, so this is how you can plot for different electric fields, magnetic fields, for example, between two north poles, two south poles, and one north, one south. Okay, and this is the iron filings method. So basically what you're going to do is that you're going to take a sheet of paper, you're going to sprinkle iron fillings on it. Okay, and then what you're going to do is that you're going to tap the paper gently with something. Okay, for example with a pencil, and what you're going to see is that the iron fillings are going to now arrange themselves in the form of this magnetic field, right? So what I did was I had a bar magnet, I placed a sheet of paper onto it, I gently tapped it, so the iron filings are now going to arrange themselves in the direction of magnetic field lines. Okay, so simple idea, magnetization and demagnetization. Okay, so you need to know what are the methods of magnetization and demagnetization. We had learned that solenoid is basically a coil of wire that has a magnetic field as that of a bar magnet. Okay, so basically it is a coil of wire, okay, which is wound around a soft magnetic material, and we know that soft magnetic material is going to be the one which can become magnetized and demagnetized both easily. right? So that is going to be a solenoid. So what you're going to do is that if you want to magnetize something, magnetize a magnetic material, you're going to place it inside the solenoid and you're going to connect the solenoid to a DC supply. Okay, so because of that, what's going to happen, that is going to induce magnetism in it, right? So this is what you can do. And then also we have, so basically we have all the methods written here, right? So for example, you have a steel bar here, right? So and you have a permanent magnet. Okay, so you can convert this to a magnet by stroking, right? So an unmagnetized steel bar is stroked several times from one end to the other in one direction with one of the poles of a permanent magnet, right? So for example, I had the steel bar, I wanted to magnetize it. What I'm going to do is that I'm simply going to take a permanent magnet. I need to have, and what I'm going to do is that I'm going to stroke my steel bar with that magnet. Okay, I'm going to lift it up, bring it back to the starting point, stroke it till here, bring it back to the starting point, then again stroke, then bring it back, then again stroke. Right. So what is going to happen is that if I'm stroking it with the north pole, and then it is going to induce north pole on my starting point, right? So an unmagnetized steel bar is stroked several times from one end to the other in one direction with one of the poles of a permanent magnet. The stroking magnet should be lifted sufficiently high above the steel bar between successive strokes. The pole produced at the end of the steel bar where the strokes finish is opposite to the stroking pole used. Okay? And then, okay, so this was my electrical method, which I was talking about. Here you can see I've connected it to DC supply. So when a large current flows through coils of wire, a solenoid, a strong magnetic field is produced. The magnetic field line aligns the magnetic domains in the steel bar. Okay, so we already have discussed what are magnetic domains, right? We know that basically a magnetic material is going to consist of magnetic domains which are going to align themselves when connected to a power supply, right? So this is what, how it happens, how a particular material becomes a magnet, okay? Because it consists of magnetic domains. If the magnetic domains, and magnetic domains are basically tiny atomic magnets, right, inside a material. So if those atomic magnets are aligned, that means it has converted itself to a magnet, right? So this is the idea what they're talking about here on microscopic level. For demagnetization, we know that we have three things. Instead of the electrical method in which we use DC supply, okay, so instead of my DC supply, I can use what? I can use AC supply. And because the direction of AC changes many times per second, what's going to happen is that it's eventually going to become demagnetized, right? And then I can heat it, I can hammer it. And the idea behind heating and hammering is that when you're going to do it in vigorously, so what's going to happen is that the magnetic domains are going to lose their alignment, right? So this is the basic idea. Okay, then we have electromagnets. Okay, so electromagnet is the one formed from a coil of wire through which an electric current is passed that allows the strength of the magnet to be varied, right? So basically you have, what you can see is that you have a soft iron core and then you have a coil wrapped around it, right? And you know that the magnetism of the electromagnet is temporary and can be switched on and off, unlike that of a permanent magnet. And why? Because iron core is basically soft magnetic material, right? And so you can, vary the strength of the electromagnet by the current in the coil, number of turns on the coil, poles are moved closer together. Okay. Okay, then we have, okay, so I've just written down the definition of solenoid, that it's a type of electromagnet, the purpose of which is to generate a controlled magnetic field through a coil wound into a tightly packed helix. But most of the times, the electromagnets that we prepare consist of large number of coils with a core inside the coil, usually a solenoid. Determining the pose of the magnet, direction of current flowing at the ends. If the current at the end flows in a clockwise direction, that end will be south pole. So we know that basically if you look at the clock, you can identify clockwise and anti-clockwise. So if the current will be moving in clockwise direction, if you can see the current moving in clockwise direction, then that is going to be my south pole. But if you see the current flowing in anti-clockwise direction, then that is going to be my north pole, right? So basically you just need to know the direction of current, whether it's anti-clockwise or clockwise. If clockwise, then south pole. If anti-clockwise, then north pole, right? So this is how you can identify. See, basically this is clockwise because it is in the direction of clock, right? And this is anti-clockwise because it's against direction of a clock, normal clock. Okay. So then moving on, we also have a right hand grip rule. For right hand grip rule, you just need to remember that you're going to grip the solenoid using your right hand. Your fingers would align in the direction of the current flow, and your thumb will then provide the direction of the North Pole. Okay. And now we're moving on to the last part, pretty much of permanent magnets and temporary magnets. We need to know the uses. Okay, all of these are uses. Okay. Permanent magnets made from magnetic materials such as steel retain their magnetism, right? We know that already, right? So can be used in applications where the magnetic field does not need to be varied. These include a compass, computer hard disk, electric motor, electricity generator, microphone, loudspeaker, and many more everyday devices such as credit and debit cards, right? So basically, we know that steel is a permanent um, it's a hard magnetic material, so it can be used where the magnetic field does not need to be varied because it's going to retain its magnetism, right? An advantage over an electromagnet is that it does not require a current to maintain its magnetism, right? And we know that we learned that in a magnet we have a coil of wire wrapped around, in an electromagnet we have a coil of wire wrapped around a soft iron core, and because of that we can vary the strength of magnetism by bringing the poles closer together or increasing the strength of current or increasing the number of coils. So because steel is a permanent magnet, it can retain its magnetism, right? So it's basically hard magnetic material. Electromagnets are temporary and are used where one wants to be able to vary the strength of the magnetic field, as well as being used in cranes to lift iron objects, scrap iron, etc. Electromagnets are an essential part of many electrical devices, such as electric bells, magnetic locks, relays, and practical motors and generators. Okay, then we have the use of magnetic shielding. Okay, so these are now basically uses of our, you know, uses in magnetism. Magnetic shielding. Magnetic fields may affect the proper functioning of equipment like magnetic resonance imaging equipment and computer hard drives. To prevent the surrounding magnetic fields from reaching the sensitive areas of these equipment, we use magnetic shielding. So you can already look at the use. Okay, so to prevent the surrounding magnetic fields from reaching the sensitive areas of this equipment, we use magnetic shielding. In magnetic shielding, thick sheets of soft magnetic materials like iron are used to divert the magnetic fields that are present. They're able to do this because magnetic field lines tend to pass within them. Within what? Within soft magnetic materials like iron. So magnetic field lines coming out of the North Pole. In magnetic shielding, okay, so magnetic field lines coming out of the North Pole prefer to pass within the soft iron sheet rather than through air. Okay, so as you can see what's happening here. So we have an iron ring. So what's happening? Magnetic field lines are passing through the iron, right? Instead of around it, right? So the field lines after passing through the soft iron are forced to come out and enter the south pole of the magnet. Region on this side of the soft iron sheet is free from the magnetic field. Magnetic shielding using a hollow iron container. The region within the iron container has no magnetic field. Okay, so all the field lines are passing through the soft iron core. Now, soft and hard magnetic materials, we know that soft can be easily magnetized and demagnetized. Hard will be difficult to magnetize and demagnetize. Example of soft is iron, hard is steel. Used to make temporary magnets, used to make permanent magnets that we already have been discussing. Magnets are used in many devices. Permanent magnets are used when a constant magnetic field is needed, right? For example, we have steel, right? Temporary magnets are used when a change in magnetic field is needed. The function of some devices, example, loudspeaker, moving coil ammeter, depend on the interaction depend on the interaction of the magnetic fields of permanent and temporary magnets. Magnetic door catches, magnetic strips made of permanent magnets are fitted on the door of refrigerators. So what's going to happen is going to help stay the refrigerator airtight, right? Keep the refrigerator airtight. Then we have, so these uses are pretty simple, just a simple idea that, magnetic door catches are using permanent magnets because a constant magnetic field is required. Okay, then we have uses of permanent and temporary magnets. So moving coil loudspeakers, a strong permanent magnet is used in the moving coil loudspeaker to provide a constant magnetic field. So basically, as you can see, what's in a loudspeaker, we have a strong permanent magnet first of all, and we know that whenever we have a strong permanent magnet, we need it to provide a constant magnetic field. Then we also have a core made of soft magnetic material placed inside a current carrying coil, which is going to become a temporary magnet, right? So the poles of the temporary magnet change when the direction of the current in the coil changes, right? So basically, what you can see is that we have a permanent magnet, it's going to have a constant magnetic field. We have a temporary magnet, which is basically formed by placing soft magnetic material inside a current carrying coil. And if it's placed inside a current carrying coil, what happens is that we're going to reverse the direction of the current, the pole is also going to reverse, right? So what's going to happen is that the loudspeaker diaphragm moves due to the alternating attraction and repulsion between the temporary and magnetic fields. So basically what we're doing is that we have a permanent magnet and we also have a temporary magnet, right? So what's that doing is that there is basically interaction between the fields of the temporary magnet and permanent magnet. Why? Because we have connected the temporary magnet to AC supply, and AC supply changes direction, right? So constantly there is attraction and repulsion between the temporary magnet and the permanent magnet. I'm going to show you the picture, wait, right? So because of that, when there is going to be attraction, the diaphragm is going to move. Okay? Loudspeaker has a diaphragm to produce sound waves, right? So when that is going to move, particles are going to get in motion. So that is how our moving coil loudspeakers are working. And then we have moving coil ammeters. What you can see is, again, we have a strong permanent magnet which is going to be used in the moving coil ammeter. A core made of soft magnetic material is placed inside a current coil, and again you can see, this is a simple idea, just like we studied for our loudspeakers. When current flows through the coil, the core becomes a temporary magnet and a turning force is produced, right? So when a current is going to flow through the core, it's going to become a temporary magnet and a turning force is going to be produced. The pointer attaches to the coil moves as the coil turns and shows the amount of current flowing through the ammeter, right? So the pointer attached is going to move according to the force produced, and force will be dependent on the strength of the current, right? So this is how it's working, right? So these were some uses of temporary and permanent magnets. Please wait for some time. I'll just, search for the picture as well. Okay. See, for example, you can see here. Is it sharing? Yes, it is. So what you can see here is, see, basically you have a permanent magnet which has a constant magnetic field, right? Then you have a temporary magnet, and this is connected to an AC supply, right? AC supply changes direction. That's all you need to know at this stage, right? So if it's going to change direction, what is going to happen is field is going to change. So because its field is going to change, its poles are going to change. At one point it's north pole, so what's happening is that it's attracting, right? At one point it's south pole, so it's repelling. So because of this constant attraction and repulsion, what's happening? The diaphragm is moving. And when the diaphragm is moving, there is movement of particles, and so a sound wave is produced, right? So that is what's happening, and that is how it's working. And this was the first part of our electricity, which is electricity and magnetism.